In this lecture, let us understand the problems on loop analysis or mesh analysis. Here, in the first problem, a network is shown in the figure. Determine all branch currents and the voltage across 5 ohm resistor by loop analysis. So, for the given network, we need to find all the branch currents and the voltage across the 5 ohm resistor. Now, for the given problem, first let us name the loop. So, we can write A, B, C, and D. So, the first loop will be A, B, D, A, and the second loop will be B, C, D, B. Now, let us write the loop current for the first loop as IA in clockwise direction, and for the second loop as IB in clockwise direction. Let us write the branch current between A and B as I1, the branch current between C and B as I2, and the branch current between B and D as I3. So here the direction of these branch currents will depend upon the voltage source that is connected. So I1, I2 and I3 are the branch current, and IA and IB are the loop current as shown in the figure. Now let us consider the first loop and let us apply KVL. Let us apply KVL to loop A, B, D, A. So if you apply KVL to loop A, B, D, A, now the voltage drop across this resistor will be 3IA. Voltage drop across this resistor, which is common between loop 1 and loop 2, is IA minus IB into 5. The voltage drop across this resistor will be 6IA. Since we are traversing from minus to plus across the battery, so we can write this as voltage rise, which is positive. So we can write across 3 ohm resistor, it is minus 3IA. Across 5 ohm resistor, it is minus 5IA minus IB. Across 6 ohm resistor, it is minus 6IA. So voltage rise across the battery, so it will be plus 50 will be equal to 0. So if we send this term towards right hand side, we can write 50 is equal to 3IA plus 5IA minus IB plus 6IA. So 50 will be equal to 3IA plus 5IA minus 5IB plus 6IA. So we have 3IA plus 5IA plus 6IA, which will be 14IA. So it will be 50 equals to 14IA minus 5IB. So let us take this as equation number 1. Now let us consider the loop BCDB. So for this, let us apply KVL. The voltage drop across 2 ohm resistor will be 2IB. Next is the battery. If we are traversing from plus to minus, there is a voltage drop, so it will be minus 25. And the voltage drop across 8 ohm resistor will be 8IB. And the voltage drop across 5 ohm resistor will be IB minus IA into 5. So if we apply KVL to the loop BCDB, we can write minus 2IB minus 25 minus 8IB minus 5IB minus IA will be equal to 0. So we can write minus 25. If we send remaining term to our right hand side, it will be equal to 2IB plus 8IB plus 5IB minus IA. So we can write the above equation as minus 25 is equal to 2IB plus 8IB plus 5IB minus 5IA. So if we rearrange the term, so we'll get minus 25 is equal to minus 5IA plus 15IB. Let us take this as equation number 2. Now we can solve this equation 1 and 2. You can solve this equation using calculator. So solving equation 1 and 2, we get IA is equal to 3.3784 amperes and IB is equal to minus 0.541 amperes. So if you observe here, IB is negative because the loop current which we have assumed is moving from positive to negative sign in the battery. Now these are the loop current values. Once you know the loop current, we can find the branch currents. We can write I1 is equal to IA. Therefore, I1 is equal to 3.3784 amperes. I2 is equal to minus IB. So why we have taken minus IB? Because IB and I2 are in opposite direction. So I2 will be equal to 0.541 amperes. I3 is equal to IA minus IB. So I3 will be equal to 3.3784 minus of minus 0.541. So I3 will be equal to 3.9194 amperes. Now you can find I3 in one more way. You can take I3 is equal to I1 plus I2 and you can find the value. You will get the same answer. Now we need to find the voltage across 5 ohm resistor. So voltage across 5 ohm resistor is 5 into IA minus IB. So IA minus IB is 3.9194. This value can be multiplied with 5 ohm to find the voltage drop. So we can say the voltage across 5 ohm resistor will be equal to 5 into I3. This will be equal to 5 into 3.9194. So the voltage across the 5 ohm resistor will be equal to 19.597 volts. So we have found the loop current, branch current and the voltage across 5 ohm resistor as required by the problem. Now let us consider the second problem. Here a network is shown in the figure. For this network, we need to find the power supplied by the source and the power absorbed by each network resistors. So we need to find what is the power that is absorbed by each resistor and also we need to find the power supplied by the source. Now before solving the problem, let us name the loop. Let us write that as A, B, C and D. Let us write the branch current. Branch current between A and B can be written as I1. Between B and C, we can call this as I2. And between B and D, we can call this as I3. Now, let us write the loop current. For the first loop, let us take this as I1. And for the second loop, let us take this as I2. Since the network is having resistor, inductor and capacitor, it is an AC network. So let us write the impedances correspond to each branch. So the impedance between A and B can be written as Z1. The impedance between B and D, let us call it as Z2. And the impedance between B and C, let us call this as Z3. And we can write the impedance across the branch CD as Z4. Now, from the circuit, I1 and I2 are the loop currents. We can write the different impedance value. Z1 is equal to 2 minus J2 ohm. Z2 is equal to 0 plus J2 ohm, because we don't have any resistance. That's why we have taken that as 0. Z3 is equal to 3 minus J5 ohm, and Z4 is equal to 1 plus J0 ohm. So here J0, because there are no AC component in the branch C and D. We are having only the resistance which is equal to 1 ohm. Now let us apply KVL to both the loops. So if we apply KVL to loop A, B, D, A, we can write. So if we start from point A, the voltage drop in the branch A, B will be equal to Z1 into I1. Voltage drop in the branch B and D will be Z2 into I1 minus I2. And we are traversing the voltage source from negative to positive. So that's why we can write that as plus 10 at an angle of 0 degree. So we can write minus I1 Z1 minus I1 minus I2 Z2 plus 10 at an angle of 0 degree is equal to 0. So if we take this term towards right hand side, we can write I1 Z1 plus I1 minus I2 Z2 will be equal to 10 at an angle of 0 degree. So this 10 at an angle of 0 degree can be written as 10 plus J0 in rectangular form. This you can remember, that will help us in our calculations. So we can write the above equation as I1 into 2 minus J2, since Z1 is equal to 2 minus J2, I1 minus I2 into 0 plus J2 will be equal to 10 at an angle of 0 degree. So if we simplify above equation, we'll get 2I1 minus J2I2 will be equal to 10 at an angle of 0 degree. So let us take this as equation number 1. Now let us apply KVL to loop B, C, D and B. So the voltage drop in the branch B and C will be equal to Z3 into I2, and the voltage drop in the branch C and D is Z4 into 1, and the voltage drop in the branch D and B will be equal to Z2 into I2 minus I1. So we can write minus I2 into Z3 minus I2 into Z4 minus I2 minus I1 into Z2 will be equal to 0. So this equation we can write it as I2 Z3 plus I2 Z4 plus I2 minus I1 into Z2 is equal to 0. If we substitute the impedances values, we can write this as I2 into 3 minus J5 plus I2 into 1 plus J0 plus I2 minus I1 into 0 plus J2 will be equal to 0. So if we simplify above equation, we'll get minus J2 I1 plus I2 into 4 minus J3 is equal to 0. Now let us write this as equation number 2. Now solving equation 1 and 2, we will get I1 and I2. Now we have equation 1 and equation 2. So we can solve equation 1 and 2 using determinants and Cramer's rule. First let us write the determinant for these two equations. So we can write delta is equal to 2 minus J2 minus J2 and 4 minus J3. So this is the determinant. Let us solve this using matrix method. So it will be 2 into 4 minus J3 minus J2 into minus J2 So this will be equal to 12 minus J6, which is equal to 13.416 at an angle of minus 26.565 degrees. This is in terms of polar form. Now we can find the current I1 by replacing the first column of the determinant with 10 and 0. So it will be 10 and 0. And we can retain the second column, which is minus J2 and 4 minus J3 whole divided by delta. So if we simplify this, we'll get 10 into 4 minus J3 minus 0 divided by delta. So we can write the value of I1 is equal to 40 minus J30 divided by 12 minus J6. So this will be equal to 3.667 minus J 0.667 amperes. We can write this in polar form as 3.727 at an angle of minus 10.305 degrees. So you can keep both the values we might need for further calculation. Similarly, we can find the value of I2. I2 is equal to, so in the determinant matrix, we can retain the first column as it is and we can replace the second column with 10 and 0. So we can write 2 minus J2. So second column we will replace it by 10 and 0 divided by delta. So we can write this as 0 minus of minus J2 into 10 divided by delta. So this will be equal to J20 divided by 12 minus J6. So the value of I2 will be equal to minus 0.667 plus J 1.334 amperes. So we can write this in polar form also. We can write this as 1.491 at an angle of 116.565 degrees. Now, in the problem, they are asking us to find the power supplied by the source. The power supplied by the source will be equal to source voltage multiplied with conjugate of current. So, source voltage will be equal to 10 plus J0 multiplied with the loop current through the battery will be 3.667 minus J 0.667. So conjugate of current will be 3.667 plus J 0.667. So we can use that value. So it will be 3.667 plus J 0.667. So if you multiply using the calculator, you will get this as 36.67 plus J 6.67. So this is the complex power. The real power supplied by the source will be the real part of this value. So the true power or real power supplied by the source will be equal to 36.67 watt. So 36.67 watt is the true power supplied by the source. Now let us find power absorbed by each resistor. So this can be given as I square R in terms of watts. So the power absorbed by 2 ohm resistor can be given as I1 square into 2. Power absorbed by 3 ohm resistor can be given as I3 square into 3, and power absorbed by 1 ohm resistor can be given as I3 square into 1. So here capital I1 will be equal to small I1 from the circuit. I2 will be equal to I1 minus I2, and I3 will be equal to I2. So here only the real parts of the value has to be written. So I1 will be equal to 3.727. I3 will be equal to 1.49 So I2 will be equal to 3.727 minus 1.49. So that will be equal to 2.237 amperes. Now if we substitute these values here, so we can find the power absorbed by 2 ohm resistor will be 3.727 square multiplied with 2. So that will be equal to 27.78 watts. The power absorbed by 3 ohm resistance will be 1.49 whole square into 3. So that will be equal to 6.667 watt. And power absorbed by 1 ohm resistor will be equal to 1.49 square into 1. So that will be equal to 2.22 watt. So this is the solution for the problem. You need to note that the complex power which we obtained can be written as S is equal to 36.67 plus J 6.67. So from this we can find true power or a real power that will be equal to a real part of S, that will be equal to 36.67 watt. So from this we can find the reactive power, that is written as Q, that is equal to imaginary part of S, that is equal to 6.67 J. Unit is VAR. If they ask apparent power, so if this is A and B, the apparent power can be written as square root of A square plus B square. So A square plus B square is square root of 36.67 square plus 6.67 whole square. So this will be equal to 37.27 VA. If you want to find phase angle, so we can write tan inverse of B by A. So this will be equal to tan inverse of B is 6.67 divided by 36.67. So this will be equal to 10.31 degrees. So from this we can find power factor, that can be written as cos 10.31. So that will be equal to 0.9839. So these are the things which you can remember. They may ask this in examination for calculation. This is about problems on loop analysis or mesh analysis. I hope you have understood the topic. Thank you.